much of the laboratory material can benefit when carrying out a practice, since by correctly using each of the equipment, the work decreases. Knowing the different pipette classification and the capacity of each one was an essential part of the practice. The pipette was used to obtain different samples that differed of volume. Given these samples, data were obtained as a mean and standard deviation that allowed us to see how good our pipetting techniques were.
Know the lab equipment and materials and the way they are organized is fundamental for the realization of experimental work, as by knowing the equipment, functionality, and applications, the number of errors committed reduce and yields results closer to the expected ones. One of those materials are micropipettes. Micropipettes allow us to measure and transfer precise volumes in microliters. There exist manual and digital volume control micropipettes, and they may use single tip, so they are called monochannel, or multiple trips or multiple channel, which allows for the transfer of multiple equal volumes in a short amount of time.
In the first activity, measurements were made using the Onisite word. 10 measurements in a minimum volume, 10 in the intermediate volume, and 10 in maximum volume. Subsequently, using aluminum foil as a container was formed and placed inside a balance, tearing and depositing the volume measurement with the micropipette P20, P200, and P1000. The weight was there. It was recorded again, and the new volume was registered until the total 10 measurements were collected. At the end, the average and the standard deviation of the three data series, which is micropipette, was calculated, and a graph was obtained to observe the error margins. On the other hand, in the second activity, a specific volume was taken in triplicate, deposited in a microtube to later record and measure the total volume. The procedure was repeated 5 times with the micropipettes of P20, P200, and P1000. Finally, the average and the standard deviation was calculated.
Registered in 3 different tables, one for the P20 micropipettes, another for the P200 micropipettes, and the other one for the P1000 micropipettes, showing variations in the weights due to possible errors in the pipetting technique, calibration, and use of the analytical value balance and the micropipettes. The data recorded for the P20 micropipettes had a mean of 0.0017 microliters at its lowest value, 0.00948 microliters at the medium value, and 0.0192 at its maximum. The standard deviations were 0.00067, 0.00043, and 0.00066, respectively, showing that the data were not that dispersed. For the P200 micropipette, the weights registered at its lower, medium, and maximum volume have a mean of 0.0209, 0.097, and 0.1969, and a standard deviations of 0.0003224, 0.001837, and 0.006299. For the P1000 micropipette, the weights registered at its lowest, medium, and maximum volume have a mean of 0.10033, 0.5053, and 1.785, and a standard deviations of 0.007991, 0.001932, and 0.0106, indicating the biggest dispersion of the values. The data obtained was graphed in order to have a better interpretation of each micropipette. For the last activity, the maximum volumes of the micropipettes were calculated and registered in a table. The mean and standard deviation for each measure were calculated, obtaining 18.966 for the P21, 120.18 for the P200, and 1003.6 for the P1001 of the mean, and 0.881, 0.2489, and 44.555 for the standard deviations.
We mainly used micropipettes and analytical balances. These are the two most used instruments in the genetic engineering lab. Knowing their functioning and means of operation of those and all of the instruments in this laboratory is fundamental for good genetic engineering practices. Besides, we also need to know the precision, because since we're handling so small volumes, the precision of a device can alter the results, since it can alter the volume entirely. This activity allowed us to analyze precision and exactitude of the pipetting. The standard deviation allows us to give us an idea of the precision of the operator of the pipette. In this case, for example, looking back at the results of the P1000, we can see the largest standard deviation. This means that the person who was in charge of this part of the practice was the least precise person. Now, these errors can be reduced with good lab practices and pipette practices. For instance, only submerging the tip of the pipette in the liquid and doing the whole motion in one continuous and slow pipetting motion.
The mean indicates the exactitude of the calibration process or the pipetting. The deviation of the mean from the expected value may be attributed to errors in the calibration or errors at the volume adjusting process by the student.
Finally, as a tip, when you stop using the pipette, you should put it in their maximum capacity so it can last longer.
During the lab practice, different water volumes were measured to reinforce the theoretical fundamentals of pipetting. Furthermore, the mean and standard deviations were calculated to question the results regarding precision and exactitude of the equipment and operators. The practice was a great practical complement to the micropipette usage concept, since measuring repeatedly masses and volumes, good pipetting practices allowed for obtention of tangible results, showing the effect of these practices have on a real result.